In this talk, we're going to introduce the basics of the processing program called TRAC, which is our Kinematic Gnss processing software. So Kinematic Gnss, this is the style of data where during the collection of the data, the GPS or GNSS receiver is moving, and depending on what that type of motion is, there's different ways you can go about processing that data. To obtain good results with this type of positioning, it helps if the ambiguities can be resolved to integer values. Although when we do this with the GLONASS system, because of the frequency switching technique used in that, we do not attempt to resolve ambiguities with those. In TRAC is a smoothing Kalman filter, and so there is a back smooth option that even if the ambiguities are not resolved to integer values, that in the final processing run, they are at least constant rather than evolving during the processing as more data are added to it. TRAC is the MIT implementation of the post-processing version of this program. There are also real-time versions, TRAC-RT and TRAC-RTB, which we don't use anymore. TRAC-RT is a real-time version. It's tricky to set up, requires internet libraries, which are getting a little more difficult to obtain. So we won't talk about this particular program in this session. TRAC, unlike many programs of this type, actually pre-reads all of the data before it is processing. And this approach has its pros and its cons. The advantage is that it is able to look back and forth through the data multiple times, resolving ambiguities as it resolves other ambiguities. The disadvantage is that it can take up a large amount of memory when you have a large, high-rate data set over an extended period of time with a relatively large number of stations. So the basic thing in kinematic GPS in general is that the success rate depends very much on the separation of the sites. And there are And also how many base stations you have versus moving stations as you go across. Our general experience is that for separations less than about 10 kilometers, this usually works very well, provided the receivers are functioning correctly and the multipath environment at the base stations is reasonable. 10 to 100 kilometers is a little more difficult, but often works quite successfully. Greater than 100 kilometers, you get mixed results, but we have run TRAC with results of separations of up to several hundred kilometers and successfully been able to do kinematic solutions with those long baselines. We'll talk about why the baseline length seems to make a large difference. Now, one thing to keep in mind that if you're dealing with not so much erratic kinematic sites, but with slow-moving sites, this is the categories of things like glaciers, landslides early on, that in this type of processing, it's sometimes better to actually use gamut than it is to use TRAC. And part of the reason is that the gamut system allows us to use many of the tools of gamut, like SH gamut, to be able to divide data up and then combine it and use it in GlobeK and generate time series that can be plotted with TSView or SH++. And so the TRAC solutions, while it has features in it which allow it to be automated and to run over many periods of time, is not as flexible as gamut is as you go through. So an interesting thing to explore if you do have kinematic data is the relationship between the individual, say 1 Hertz positions of a site and what the value is when you process it with gamut as a combined 3-hour or 6-hour chunk. And what you tend to find is the gamut solution pretty much lies at the average of the values that you're getting from your kinematic solution. And so if it's a smooth trajectory being followed, the gamut solutions provide a very nice way of representing that motions. So if you do it with the gamut solutions, depending on how fast your object is moving, you put in the velocity into the a priori coordinate file. Here we're specifically thinking of, say, ice sheets, for example, which might be moving at rates of up to 100 meters per year, for example, which would be 30 or 40 centimeters each day. And then in SH gamut, there's an option of the SES info, This is the session information option. And this tells SH-Gamut how long each data span should be and what should its start time be. And so you can have multiple chunks of data, say 3-hour chunks of data over a day, and you can specify the start times of each of those days. And then you can use the netextend option to put each of those sessions into a different directory. And then generally, the easiest way to do this is to run the first session of the day to download the Rhinex files and generate G files of that nature. And then in the subsequent parts of that day, use no FTP, so it doesn't go and check to see what Rhinex data is available. And the make G option to be no, so that it doesn't keep remaking the orbit file for each one of those days. The only caution you have to worry about here is that in our standard process.defaults file that controls types of things that get processed, we do have a minimum X file size, which is designed for 24-hour sessions of data, so that if you have a 24-hour session in which there's only a couple of hours of data, that session won't typically get processed in SH-Gamut unless you set this min X file size down to be a lower value. You might also look a little at the trim one-way command in the autoclean.command file so that you don't excessively throw out data because of the short spans that are involved here. Trim one-way basically sets limits on how much data needs to be available for a particular segment of data to be retained in the solution. And always you can actually use track for this type of analysis as well. So this issue with the length of the station, so the separation between your sites, it has major impacts primarily because of the differential ionospheric delay and the differential atmospheric delay between those sites as you go through. In modern data, the degradation in positioning because of the orbit quality is a very, very minor contribution to the degradation with increasing baseline lengths. So when you have short baselines, less than 2 to 3 kilometers, for example, the ionospheric delay can be treated as approximately 0. And you can use the L1 and the L2 ambiguities can be resolved separately rather than in the linear combination, which has removed the ionosphere. You can then also do the positioning with L1 and L2 separately, and this will reduce the amount of random noise that's in your solution. Because as we mentioned early on in this course, the dual frequency combination that eliminates the ionospheric delay increases the noise in your phase measurements and increases contributions from things like multipath, for example, by typically factors of 3 or so. So when you go to longer baselines, this is no longer true, and you cannot treat L1 and L2 as being the same range measure with just a different ambiguity on it. And then you want to use a linear ionospheric free combination, and track is going to use the Melbourne-Wibbiter wide lane to resolve the number of L1 minus L2 cycles first. And then having resolved that, look at what its best estimate is for the number of L1 cycles to allow it to calculate both together. It also uses an ionospheric constraint type model, which we'll talk about in a second. And to help that, then you can read in these ionospheric models, global ionospheric models available typically from the IGS and some of their analysis centers, to give you an a priori estimate of the ionospheric delay on the long baselines. And that can certainly help as well in bringing the ability to resolve ambiguities into a better approach. In both the long and the short baselines, and particularly in the short baselines, you can resolve ambiguities using the ionospheric combination and then set a solution in which you use just L1 and L2 separately or together, or you can switch it around and resolve the L1, L2 sample ambiguities and then do an LC solution. So there's multiple data types that can be used in the output. So when you're dealing with these short baselines, it's a good idea to try the different combinations just to see how much your results are affected by it. So the features of track itself, as I said, it uses the Melbourne-Wibbiter wide lane to resolve the L1, L2 differences, and then a combination of techniques to determine the L1 and the L2 separately. So basically it adds what we call bias flags at times where there are cycle slips, and then the ambiguity resolution tries to resolve those cycles to integer values as you go through, and if it is able to, then the bias flag is eliminated. So it uses a floating point estimate of the ionospheric free bias, and then the Melbourne-Woburner wide line that tells it the difference between L1 and L2, and an ionospheric delay constraint. So that has three types of information, and from those three pieces of information, it tries to balance them and come up with its best estimate of the L1 and the L2 cycles, which it then determines whether it can resolve to integer values or not. We use Kalman filter smoothing in here, although for many kinematic position estimates, we simply make the kinematic position very large process noise so that it is actually not really smoothing, it's simply generating a value at each of the epochs independently. But the nice thing about the smoothing is that any non-resolved integer parameters, they're constant in the run. And then the atmospheric delays are also consistent with the level of process noise that you had as you specified in the command file as you go through. And so whenever you're estimating atmospheric delays, the smoothing option should always be used. So to resolve ambiguities in track, it uses what's classed as a relative rank approach. And so relative rank is a measure where you look at the chi-squared difference between your best chi-squared value you can have by making an L1 and L2 integer values. So as I said earlier, we have these three measures of what the number of cycles should be in the combinations of the L1 and cycle. So Melbourne-Woburner wide line tells us the difference between the two. We average that over a reasonable amount of data, depending where the bias flags are. We have an ionospheric free estimate, which is a combination of the L1 and the L2 ambiguities. And we have this ionospheric constraint estimate, which again is a combination of the L1 and the L2 estimates. For each of those quantities, we have an estimate of its uncertainty where we try to take into account correlation in the time series, temporal correlation in the time series. And so with those estimates, as we try to make the L1 and the L2 values be integers, there's a difference from what is implied by the data, and we can compute the chi-squared value of that increment. So in track, we try a number of choices of those integer values around the best estimate that we have, and we keep track of the chi-squared, and then we look at the best choice for the chi-squared increment and the next best choice. And if that ratio is high enough, then we will say that we are potentially able to resolve the integer ambiguities. And then we also look at other measures of the level of scatter, the amount of actual chi-squared change, the sigmas that are involved, to make a final decision as to whether the floating point values can be reliably converted into an integer value. And so the quantity, we just call it the relative rank RR, and as the larger that value is, the better. So the chi-squared is computed from this match of the LC combination, the Melbourne-Woburner wide line average values, and the closeness of the ionospheric delay to 0. And that's where putting in an a priori ionospheric model can be useful, because if it's an accurate model, then it will be give a better estimate, which is closer to 0. We can change also the relative weightings between the Melbourne-Woburner wide line and the ionospheric delay. And in particular, when you go into long baselines, longer than 100 kilometers or so, we typically will downweight this particular contribution to give it less weight. So because the ionosphere could be larger on those. And that's what's the relative weight setting that we go. So these estimates are iterated. And so as we resolve ambiguities in one pass, we resolve the ambiguities and then propagate that resolution through the covariance matrix of the solution. We do that until we cannot resolve any more ambiguities. And then the whole solution is repeated again, regenerating new estimates of all of the ambiguities from the actual raw data. And again, we try to resolve the ambiguities in that new solution. And we keep going until we either reach a maximum number of iterations or we run out of ambiguities to resolve. So the Melbourne-Woburner wide line, we've talked about a number of times. And again, this is that difference between it's basically the difference between the L1 and the L2 phase, where the L2 phase, so the Melbourne-Woburner wide line is the difference between the L1 and the L2 phase, where we get an estimate of that from the shooter range. There is also a measure where the L2 phase is scaled to the L1 wavelength, and that's sometimes simply called a wide line. And both of those can be used to try to detect cycle slips. However, this second one where you scale one phase to the other is sensitive to fluctuations in the ionosphere and is inversely proportional to the frequency squared. So again, the L2 lower frequency has a larger ionospheric contribution than the L1. So the Melbourne-Rubin wide lane removes both the effects of any geometric changes and also any ionospheric changes that have taken place in the range, and it uses the range values to do that. So the characteristics of that Melbourne-Rubin wide lane is that in one ways, in other words, just a single station to single satellite, it can be computed with the raw phase measurement and the raw range data that comes from your receiver. But because of things like antenna phase center models and other quantities where the transmission phase center position is a little different for L1 and L2, we generally compute it with the difference between the observed phase value and the computed phase or the computed range value as we go through. In one-way form, it does not necessarily need to be an integer unless you have fractional biases included in your calculation. For groups that are doing ambiguity resolution in precise point positioning, that's one of the critical files that is needed, is the phase difference for each one of the satellites and each of the observable types that you're using. We've also found that there often is slopes in this data as you look at it over time, and we'll see that in this example on the next slide. This is one of those things, again, where the phase calibration of the antenna, for example, we do not apply any range calibration for the antennas. And so there is expected to be some differences as you change elevation angle due to those phase models on the antenna. So if you have a satellite pair difference from another station, and it's particularly when it's the same brand in the receiver, those are subtracted, then the results are likely to be integer. And hopefully the difference between them should be close to an integer value. So the Melbourne-Rubin tells us the difference between the L1 and the L2 cycles. And then to get the individual L1 and L2 cycles, we need another technique, which we briefly described in the previous slide. Interestingly, and this is something that might be potentially useful with systems, the more modern systems such as Galileo, there is an equivalent formula to the Melbourne-Rubin wide lane, which is where you sum the L2 and the L1 phase cycles. But when you do that, the range noise multiplier is about a factor of 10, as opposed to a factor of 0.1 when you do it for the Melbourne-Rubin wide lane. So we actually have computed this quantity, but for GPS solutions we've tried, the accuracy of the range data has never been adequate for this to be a particularly successful technique. So the next slide gives us an example of what these look like for two GPS satellites, PRN7. This is from a single station. And so the black curve is refers to the curve on this side, and then the dotted line refers to this. And then these dark lines running across on both of these scales are one cycle apart. And the numeric values here, as you see, are large. With older generation receivers, that's what you tend to see. I must admit, modern generation receivers tend to initialize their phase values based on the pseudo range value. So for modern receivers, these numbers are typically much smaller. But these are one cycle apart, and you can fairly easily see that if I was to difference these two between this, not only would I remove the slope in the results, but I could make a very reliable estimate of the number of cycles between the L1 and the L2 phases, which would be the differences between these two numbers. The absolute values you might notice here are quite substantially different. So the actual formulation for the Melbourne-Rubin wide lane is L1 phase minus L2 phase. And again, normally because of the difference in wavelength, this would be a strange varying. You would see geometric changes in this quantity as well as ionospheric changes. And then this factor that you subtract from it, which is the sum, interestingly, of the L1 range converted to L1 cycles and the L2 range converted to L2 cycles, that sum and the combination of the difference of the frequencies and the sums of the frequencies, that when you subtract that from the two L1 phase measurements, you're going to eliminate the change in this difference due to both the geometric change and due to any of the ionospheric effects that are happening. Now that difference in some frequency pair, delta F over sigma F for GPS, is about 0.12 for the standard L1, L2 channels. For the other GNSS constellations, the number is of the same order. The one big difference would be for the Indian Iridium system, Indian IRNS system, where they use S-band, and that would be a substantially smaller number for that system. But as I said earlier, we don't really have data from that system that's useful at this point. So it should be an integer within noise, and typically when you do this, you average it over periods of time where you have a sufficient data to remove some of this high frequency noise, for example, you can see. And you can see even in this data, by the time I get down to low elevations on this satellite, there's enough noise in here that I'd want to be averaging a fair amount of this data to make sure that I was actually getting a reliable estimate of the integer value. Now, when you do this also, if you're mixing receiver types, you do need to bring in the dcb.dat file, which tells you the bias between the L1 pseudo-range and the L2 pseudo-range measured with a P-code tracking versus a cross-correlation tracking. This differential code bias tells you what that is. And again, since you are summing the range values here, a constant offset directly goes into these values, and that's what you have to account for in the differential code bias file. So the other quantity which is used in track is what we refer to as the extra wide line, or EXWL, and you'll see these abbreviations used in the outputs of track. And this is just the difference in the L1 phase minus the L2 phase scaled by the wavelength of the ratio. So this ratio basically means any geometric changes between the range in the spacecraft and the ground station, or the ground station moving, will cancel in this difference. And if there is no ionospheric delay, then the only thing that this would have, it would have the n number of L1 cycles and then the number of L2 cycles multiplied by 1.28. So the L2 cycles are not integer in this particular form. And that's what we take into account when we're doing the ambiguity resolution and comparing the observables as we go across. So this is independent of geometry. It's interestingly, when you're looking at one-way data, it's not independent of the orientation of the ground antenna. And so one of the corrections we've never applied to track, although we're thinking of doing it, is that in one-way processing in a moving vehicle where the antenna is rotating, if you rotate a GPS antenna by 360 degrees on the ground, the L1 phase will change by 1 cycle and the L2 phase will both change by 1 cycle. So even though there's no ionospheric delay and you haven't changed geometric position at all, this difference will actually change by 0.28 cycles when you do that. And so to be able to apply that correction, you need to be able to keep track of the orientation that the antenna is pointing in. And so again, on short baseline separations where the ionosphere is small, this is a very low noise measure of the number of cycles, and we often use it instead of the Melbourne. We would give it a weight similar to the Melbourne Movement of wide lane as we go through. So one of the classic problems you have in track when you're doing bias fixing is that the most common type of error that we're going to make is where we have the same number of cycle slips at L1 as at L2. We often refer to this as a 1-1 slip. And in a 1-1 slip, because the Melbourne wide lane won't change at all, because it's the same number of cycles at the two, this EX wide lane will change by about 0.28 cycles, which is about 53 millimeters. And to give you an idea of the magnitude of that in terms of tech units, this is about 82 millimeters of L1 ionospheric delay, which is the equivalent of a half a tech unit. And so the ionospheric delay can be many tens of tech units. And so how fast the ionosphere is changing and whether 53 millimeters is small or large compared to the rapid change in the ionosphere, that's what is limiting the use of the EX wide line. And on short baselines, it's generally nowhere near this magnitude, and that's why it's very successful. So the basic inputs that you need for track are, you need a set of observation files. These are RINEX data files, RINEX 2 data files. We have not yet upgraded track to read RINEX 3. That's on our list of to-dos as soon as possible. And you specify whether the site is kinematic or fixed. And again, we recommend that the first site be the fixed site. We recommend that that site be a high quality site with small multipath if you have a choice in the subject, and that there only be one fixed station. The reason is that the fixed stations are absolutely fixed. No coordinates are estimated for those. So if you've got a bad a priori coordinate for one of your fixed stations, it will corrupt the solution. So you need the observation files, and then you need a navigation file, which is either a broadcast ephemeris file or an SP3 file. And these days, generally, we use SP3 files. And then they have SP3 at the, as the option at the end of the line when you do that. There's a quick shorthand mode setting command, which sets various a priori parameters of what weight things are given, etc. And that's either air for aircraft, short for short baseline, or long for long baselines. Most of the time we work in the long baseline mode. Air is not, is very similar to long these days. It really just has potentially larger process noise associated because of the rapid plane motion of the aircraft. And again, once you've set this, you can then go and upgrade the commands as you wish after that. Normally, we recommend that you have the backtype smooth option turned on. That ensures that you do the forward backwards Kalman filter to smooth the results as you go. Our strongest recommendation is that when you start, you pretty much just use those 4 commands and see what comes out of track, and then look at the interpretation of the track to see whether you need to fine tune anything as you go across. So we start with that, and then generally, so the simple command file is track, and then -F is the option to specify the command file. You send the output into a output file. This is the C shell format for doing this. The ampersand means that the error messages go out there as well. And then you do a quick quality check. You can do a grep -E, or this is an egrep, where it is, you're looking for any line that starts with phase RMS and then type, and then this on the summary file that comes out of track, or on the track output itself. And what you're getting here is for the individual sites, you're getting told what the RMS scatter of the phase residuals is. And for this particular solution that was run in here, there was multiple stations, and they were 7 millimeters, 7 millimeters, and 7.4 millimeters for the LC combination. And then these are the RMSs by individual satellites. And this looks very good. 7 millimeters is actually quite good. Anything below 10 millimeters for a kinematic positioning is considered a good result. Anything below 20 millimeters is generally not too concerning. Again, when you're in a kinematic environment, particularly if it's, you know, ocean buoy or something that's moving around, you're moving through the phase center model of the antennas. There's lots of things happening. The tracking loops don't necessarily track as well as you might hope as the instrument's moving. And so it basically is an indication that your phase noise is generally a little larger. And these are also single difference phase noises. So this is really the noise between the base station and here. So these should be square root of 2 larger than a phase noise you would have out of autoclean, which has resolved the phases back into single satellite to station residuals. You can also check the keyword kinematic in the output file. And the idea here is this just tells you what your coordinates are behaving like. So it says in this particular station that this USM3, which was said to be a kinematic station, appears to be static. And that's because its RMS coordinates based on the shooter range only solution are down at a couple of meters. And the a priori coordinates actually match within 50 centimeters or so of where we think they should be. The MIT-B, which was the base station of MIT, also seemed to be kinematic and seemed to be static with very small weighted RMS. And then, not surprisingly, the kinematic site called Rover, which was the moving site, was dynamic and has RMS coordinates of 17, 18 meters, etc. These data are from a test experiment that we run at MIT on one of the athletic fields. And you can run this through this site at the end. You want to just head the results, because after the first pass of this, these results all go basically to 0 because it's basing it, it's already got an a priori trajectory in place as you go. And then you can check the track summary file to look at the status of the ambiguity resolution. So we'll come back and look in more detail at how you work out ambiguities. But the basic track command file looks like track run string, looks like the command file, and then an option of putting in an ambiguity file. We'll talk about how you do that in a second. And then you can have this -d option in which any string which appears inside of your command file, which has day in it, that will be replaced numerically by whatever this numeric value is. And then -week, any place where you have week in here, it'll replace that with that numeric value. This is implied to be GPS week and day of week, but these are actually just simply numeric values that get replaced. So you don't have to use them in that mode if you don't want to. And then we have the more flexible one, which is just this -s option, which allows you to specify a set of strings, which everything in your command file, which has left bracket S01, right bracket in uppercase of this type, that will be replaced by whatever the string is that you put in here. And again, we typically use this to allow us to have flexibility in naming summary files. There's one special case in here where if the word you have is the word space, S-P-A-C-E, it'll actually replace it with the blank character at the start of the line. And that's a way you can uncomment lines inside of your command file. So again, this is optional as we go through. And so when you have this sort of format for base 1, day 030, for example, that's going to be replaced with the 122 as we go through. So as I pointed out, with use of the word space, you can make this a blank line and have it go through. So for checking ambiguities, the simple way to do that is just to grep on the word final in the summary file. And then that's going to give you column data, which lists all the ambiguities. And there's one column which is labeled fixed FXID above it. And if it has a numeric value 3 in it, it means that that ambiguity was successfully fixed to an integer value. If it has a 1, it still means that it's a floating point value as you go through. And then we'll see that there's also going to be indications of why it was not fixed to an integer value as you look in the track file. And that's the tuning part, is to look at the ambiguities that were not resolved to integers and try to understand why that did not happen. So the output types that you can have are many different types. There's a northeast up output, which is quite appropriate for short baselines, 10s, 20 meters, several kilometers. And it's just going to be the north and the east and the up difference in position between the base station and your moving station. And in this case, north and east are resolved based on the latitude of the base station itself. You can output geodetic coordinates as geodetic latitude, longitude, and height. We do this when we want to put the kinematic trajectory, say, into Google Earth as a KML file. There are shell scripts that will convert track output to KML. DHU is differential height, horizontal, and up coordinates. It's a very similar looking format to the NEU, except that it's in millimeters, and it is the difference from the a priori coordinate that you gave for that particular station. This we particularly find useful when we're doing seismic wave arrivals, for example, and we want to look at the surface wave variations. You can also give it Cartesian XYZ coordinates, which are useful if you want to carry out your own particular numeric calculations with the results that are coming out. In theory, you could convert Geodetic to XYZ and vice versa if you wish to. So, and the units here are meters for these quantities, millimeters for DHU. Geodetics are in degrees and meters. So track has a very large help file associated with it that explains strategies and how to interpret the outputs, etc. And so that's what you want to read as you fully more explore the way that track actually operates, and it tries to explain the outputs and how to interpret them. As we mentioned earlier, it's possible to read in ambiguities into track, and you do that by simply extracting the final lines from the track summary file, and you put them into a file which you name the ambiguity file. We normally end it in .amb, for example. And then, depending on what you want to do, if you think that the value that the track had actually resolved was the correct integer values, but it just simply didn't know that it was the correct integer value, you can replace the 1 in the fixed column with 7. And again, to allow it to differentiate, in theory, you could put 3, but we also put 7 in just to make it clear that it's a manually put in value. If you're feeling very ambitious, you can actually change the ambiguity number of cycles and track will use what you tell it to do. That's sometimes interesting if you want to see what is the impact of making an error in resolving an ambiguity in your output as you go through. And you can read this ambiguity filing with either the -a option in the track command string, or there is an ambin file, ambiguity in file command that you can use where you would actually specify that file name. The first form is a little bit more flexible as we go across. So those are the very basic features, but now there's also a lot of advanced features that you can use, and you can control how biases are fixed in data as editing. And again, editing is a little tricky on moving platforms because jumps in phase could simply be movement. And so that's where these wide lane measures, the Melbourne-Rubiner and the EX wide lane are useful because they don't depend on the movement of the platform per se. And so you can use that as a measure to see whether you have cycle slips. And as I said, you can use that EX wide lane. And then there's also Explicit Edit Svs, which is site satellite commands, where you can actually remove specific pieces of data. We find this sometimes when we are doing kinematic work around campus. We will have obstructions near where we're working, and there are just some segments of data that are short and not well represented, and it's just as easy to manually delete them from the time series rather than having track try to automatically delete them. You can also explicitly add and remove bias flags as well, if you wish to. So the commands that people start tuning fairly rapidly is this group of commands here. The BF set command, which is bias flag set, really is specifying how big a gap in the data do you allow before a bias flag is automatically added to it. The default is 1, and the assumption in the default is that if the receiver misses a data point, it has lost lock on the signal, and therefore there is going to be a cycle slip. In practice, we've found with high rate data that is not a good assumption, and that receivers, even when they're tracking internally, we have noticed often have data gaps in them, even though there is no cycle slip across that gap as best as we can tell. And so often we push this number up to a factor like 3 or 5. The longer you go, the more careful it has to be in actually detecting whether the cycle slip occurred across that gap or not. And then the minimum good, which people normally don't change at all, you can just give the one argument if you wish. The minimum good value is just what's the smallest span of data that you're willing to try to resolve ambiguities on. And again, that generally, you would like to have, particularly say with 1 Hertz data, you would like to have at least 120, a couple of minutes worth of data just to be certain that you can resolve ambiguities on it potentially. The other command, which often gets modified, is the ion stats command. And this is really telling the software how big a jump in the EX wide lane will be interpreted to be a cycle slip. And again, you have to be a bit cautious of this in low elevation angles because there can be, because the noise level in the phase is high at that level, there can be discontinuities in the phase values which look like they are cycle slips, but they're really just noise. But in other cases where you have a lot of ionospheric activity going on, again, there could be potentially cycle slips embedded in jumps and places where it appears to be jumps, but they're not, just simply because of the ionospheric variation. So if you're in polar regions or in equatorial regions, this is one of the commands that you might play around with a little bit more. The command that just about everybody modifies almost instantly from the default values is the float type command. And it's the beginning parts are okay. This is the, it's going to basically do a floating point estimate of the number of ambiguities. And this is controlling how it uses that to do ambiguity resolution. And so the start and the decimation values are simply what epoch to start accumulating the information about the number of cycles. That's almost invariably the first epoch. There's very few reasons to not do that. And then the decimation is how many data points do you want to use in trying to do it? And when you have 1 Hertz data, or say if you had 10 Hertz data, to speed up the processing, you might actually decimate that to 10. So it's actually using 1 Hertz data to do the floating point estimates, and rather than the whole full rate data. Again, most people would just leave that as 1 using all of the data around. And then the type is whether it's an LC, which is the ionospheric free floating point 1, or L1 plus L2, where the individual values are separately resolved. Most of the time, even on short baselines, we use the LC type algorithm just because that's the one we use most, and that's the one that has the highest level of checking and processing subtlety associated with it. Now, the numbers you do tend to change fairly rapidly are these floating point sigma limits. And the reason you change them is because inside of track, we have built in estimates of temporal correlation characteristics in the data. And this is particularly important when you say have 10 hertz data. If you have 10 hertz data and you have 10 seconds of data, then you have 100 data points. If you take the average of that, it's going to rapidly average down to a white noise value, 1/10 of whatever this RMS scatter is. Experience tells us from phase data, and you could see it in the Melvin-Rubiner wide lane plot we saw before, is that things are not white noise necessarily. And so we have built-in correlation constants that are there. And that's one of the reasons when we change the decimation, it doesn't really change the signals very much, because when you're using 10 hertz data, for example, most of that 10 hertz data is within the correlation limits that we have, and therefore does not really help contribute to the standard deviations. Now, we set the float sigma that we use to be conservative. And so when you are looking at why integers don't get resolved, one of the most common reasons is because the standard deviation of the estimate was too large. And so the easy fix to that is simply to allow it to resolve ambiguities, even though the sigma appears to be large. And then you can do that for the LC estimate and then for the wide lane estimate, in the Melvin-Rubiner wide lane. And again, it's usually the Melvin-Rubiner wide lane where the limit is actually a half a cycle, but we find that one cycle is still perfectly adequate, even though it sounds like it should not be. And that's because we're taking into account correlation, and that correlation information we have is sort of a worst case scenario. Most data is not as correlated as our algorithms assume it is. The other ones that you can play around with is the weight that you give to the Melvin-Rubiner wide lane and to the ionospheric estimate. And again, on long baselines, this automatically gets downweighted to a small value. And if you have high ionospheric activity or your ionospheric model is not particularly good, you can make this a much smaller value to give less weight to the ionospheric delay. In some cases, we've had where we've actually downweighted the Melvin-Rubiner wide lane because for the particular brand of receiver that's being used, there's smoothing put on the shooter range data. And so the statistical characteristics of the wide lane look smoother than they are in reality as you go across. And then the max fit essentially is a measure of what's the largest chi-squared that you will allow to happen and still resolve the integer ambiguity to its value, even if the contrast is really high. And then relative rank is the final relative rank value. And again, we sometimes, the value by default is fairly conservative. And so if you want to be more aggressive in ambiguity resolution, you can make that value lower. The way you work out how to do all of those things is through the F-code diagnostic, which comes out in the bias flag. And we'll talk about that in a second. So finally, if you want to be, if you think track has missed an ambiguity, which it sometimes does because of various reasons, and you can't get it to automatically detect it because it's a complicated geometry where it's not necessarily on the satellite's a satellite that it thinks it's on, you can explicitly add a bias for a site and a PRN number and a specific time at which it occurs. Now, sometimes also track will add bias flags, and it's hard to tell it not to add them. And so you can also delete bias flags if you like as well. And so these two commands are very useful. Again, we try to avoid using them because it makes the command file then be very specific to a data set. And we like, as we do in GlodeK, to have the command files to be somewhat independent of the data that you are processing. Okay, so the track outputs that come out, generally you redirect the file, we call it into something generally just out. There is a summary file that you can specify the name of. If you wish to, the default name is track.sum. There's the position files in northeast up, geodetic, differences in northeast and up, and then XYZ. You can output the phase residual files if you wish. Those can get quite large. And you can also output the Melvin-Rubiner wide lane, or the wide lane files, which contain both the Melvin-Rubiner wide lane and the EX wide lane as well. And then the help file basically tells you what's in some of those different files. So the summary file is really the place you often start with looking at the output file itself, because it's an iterative solution and it iterates a number of times, can be quite large. So generally look at the output file and have the, it tells us things about how we ran it, what process noise, any editing we had. It has this final bias flag report, which is the thing that we're going to use if we're going to do ambiguities, etc. And it has summaries on the residual scatter and information about how well the position estimates were repeatable, etc. So again, the initial status comes out. So the types of information you get as the files are read. The most common problem people often have is that there is no sampling rate given in the Rhinex file. And so you can specify the interval command to tell it what the sampling rate is. The other thing you can also do is if it's a 1 Hertz data file or a 10 Hertz data file, you can set the interval to be 30 seconds, for example, and it will process just the data every 30 seconds. We find that a very useful thing to do, to just get a sense on a data set as to what the quality actually looks like before going into the much longer run using all of the data that's available. So Track first does a shooter range solution for the trajectory, and that's where it decides whether the site is really kinematic or not. There's no real difference in there, except that if it thinks it's a static site, it will use just a single set of coordinates for the site for the processing. If it thinks it's kinematic, it will actually have a trajectory of those coordinates as it goes through. It then looks and scans through the data to check for bias flags and whether jumps are uploaded. It checks for any bad prefit data. So essentially, if it's when it's trying to fit the trajectory on the shooter range data, there can be bad shooter range data, etc. And then the summary of the bias flags is needed, and it estimates the number of cycles, and that gets reported in the initial estimate. So while averaging the data, it's looking at the Melbourne wide lane, and it's using the ionospheric, and it's coming up with an initial set of cycles for L1 and L2, which it outputs. And then it also has the mean estimate of the ionosphere in that, and the correlation. As I said, correlation time is assumed in doing the calculations of the standard deviations of these quantities. So it simply does not take the RMS scatter of the Melbourne wide lane, for example, and divide it by the square root of the number of data points to come up with an estimate of the uncertainty in the Melbourne wide lane. It's taking into account time correlation on a fixed time correlation model to come up with those stigmas. And then you can actually look in detail. There is this DD bias reference for each one of the one-way elements in a satellite to ground station to satellite. It will tell you what the 3 other one-ways it used to come up with that estimate of the double differences. And you'll see later on in the runs that sometimes it'll actually move those values around if it thinks it can come with a better choice as we go. Okay, so Track does this iterative solution where it tries to resolve the integers, and it has floating point estimates that are coming from its estimate of its trajectory. It has the RMS fits of the double difference residuals, and it's also reporting any double differences that it throws out because it does not think it's consistent. If you see a long stretch of phase data being thrown out, sometimes that's because Track has missed a cycle slip in the data somehow, and you might have to manually go back. And then it's going to have a bias fixing report, which will have a column which is labeled either true or false to indicate whether it thinks the bias has been successfully fixed. And then this F code in the column, which we'll look at in a second, is the thing which tells you why it was not fixed. And that sequence gets repeated until it runs out of ambiguities to resolve. And then once it's done that, you can specify what types of data combinations do you want the position estimates generated from. So even though you ran an LC ionospheric free solution to get the biases resolved, you can then tell it to run the solution just using the L1 data, just using the L2 data. And again, on relatively short baselines, that can be an interesting quantity to look at. We clearly often see that there are substantial biases between the L1 and the L2 solution, which we think, again, are related to phase center calibration issues on antennas. Now, the thing which comes out in the bias flag report, this gets a little tricky to show because it's actually a wide line and it's wrapping on this screen. So this line actually continues across. The font would be too small if we tried to put it all in one place. But it's basically telling you the bias flag number here. This is bias flag 172. It is to site number 5 using PRN 15. It starts at epoch number 1 and actually only goes to epoch 43, so it's quite short. It is currently a floating point bias, and here is the estimate of the ionospheric free combination of the bias, 1.86 cycles, and that's plus or minus 0.24 cycles. And then the signal limit, which is this L requirement at this point, is 0.25 cycles. So this would be resolvable to an integer because it is less than the standard deviation. But the relative rank on this one is only 2.36, which means that it is not well enough to separate it from its next best choice for it to be resolved. So its fixed status is false. And again, with only 43 epochs of data, that's not surprising. And then this is the estimates of the L2 cycles that it would have and the fit parameters that go with it in terms of the ionospheric, wide lane, and the LG. So you can see the LG on this is already quite large, 105, and that's potentially, it's being downweighted, and this is a long baseline case. So this F code quantity in here, which has these dash dash R, the R tells you that it was the relative rank, which meant that this was not resolved. The next one in this little example actually has, again, a much longer span, 10 times the length of data spanned in this case. It's somewhat later in the list of sites. Again, the estimate is near 0. It's 0.74 uncertainty, and it actually has a very high relative rank compared to the next best choice of the ambiguities. And the choice we're having here is 0, 0. So it thinks whatever its value that it's currently using is the correct value. And it's not being resolved to an integer because the S column says because of sigma, but also importantly, the O at the end means that it is not resolving this to an integer because the particular double difference combination it's using for this calculation, some other one way in that double difference combination has not yet been resolved to an integer yet. So it's going to wait. And so later on, when that other one that it thinks can be resolved to an integer is resolved to an integer, this value will come back, and now that O will not be set. So this is the scheme. You look at the F code. The other columns, we'll talk about in a second in here, can be W, which means the Melbourne Rubin wide lane is too poorly determined, has too large a sigma on it. That's a very common one that we often change the status for just to have it happen. So these F codes indicate how the ambiguities were tracked and importantly, why they weren't fixed. So the S and the W indicate that the sigmas were too large, and those can be changed with the LC float command to make them larger so that they will be resolved to integer values. And if the relative ranks are large, then you can change them in the float. If the ambiguity seems to have the same value as the other ambiguities around it, and that's actually fairly common, we tend to be conservative again in detecting cycle slips or if there's gaps in the data. Even though, and if your estimates all come out to be the same basic value, even though the track could not resolve them necessarily to an integer, you could actually delete that bias flag out in the command file, or you could use the ambiguity file to absolutely fix it. Again, as with much of the software here, there's typically multiple ways to achieve the same things. And so if the chi-squared increments are too large, that's generally associated with the ionosphere as our experience, although with stations that have poor tracking receivers, sometimes it's just the geometric solution is not very good either. And so you can downweight the ionospheric contribution using the float type as we go through. So starting in version 2.1.26 of track, we're currently at version 1.41, we have actually the ability to read global gridded ionospheric models, and you input that in with the ionospheric file command. The reading of these files pretty much is set on the time spacing, etc. of the IGS products. And so if you want to cross day boundaries, for example, it gets a little tricky when you're using these files because you have to generate a file that actually crosses the day boundary and has everything in the one file. So you have to do a bit of manipulation of the individual files that you have. And again, the EX wide line is the quantities that's affected by this. And this is very useful for baselines longer than about 100 kilometers or so. As I said, in some cases, you can do the manually supply the ambiguity file for track. The most common case we use this for is when we're doing earthquake studies. We may be, some large earthquakes, to have a base station which is not affected by the earthquake needs to be far away, often several hundred kilometers away from the site. And since most of the time the site is a static site, we will run track where we have zero process noise on the site position, except for a few minutes around the time of the earthquake. And then in that solution now with static site coordinates, most of the time, the ambiguities are more likely to be resolved to integers. So we'll run that solution and then use that ambiguity set as the input to a run for track where we now have process noise turned on for the whole span of the data. And the turning on for the whole span allows you to get a measure of what the noise in the time series is before and after the earthquake. And if you wanted to look at things like sidereal filtering, for example, for GPS type solutions. And you can get that essentially, as we talked about, by grepping out track. We also have some recently added commands, which came in at version 1.40. This was the 10.71 release of track. Most of these changes are due to our colleagues in Tasmania and Australia, who are doing a lot of ocean buoy work and find this useful features to have. There is a use BLQ command, which turns on ocean tide modeling for the site. So you can, if you're floating on the ocean, you can actually have a model which automatically takes into account that you're actually moving in that way. And it requires a site.blq file to be available. The formats of those files are the same as they are for the gamut tide models that you use, the site-dependent tide models. In this option now also you can turn on the solid earth tide and turn it off, and actually two different versions of the solid earth tide if you want to see how those tides affect your kinematic tracking. There's also a new command called ATM model C. It actually replaces the use GPT GMF command and has the same options that this command had, but also the options to read in the atmospheric delay models that can be used with the VMF1 grids, for example, that you'd use in your gamut processing. And those are actually very useful for getting your atmospheric models as accurate as you possibly can during your kinematic processing. Oops. So the other tunable parameters, that if the process noise and atmospheric delays, you have to remember critically that if you have kinematic sites moving in vertical, then the height estimate is going to very highly correlate with your atmospheric delay estimates. And in particular, if you have not only a static site that you're treating as kinematic, if you plot the height variations and the atmospheric delay variations, you'll typically see they're extremely high correlated together. So you might want to think about making your atmosphere a little more constrained to improve the repeatability of your height estimates to go. And again, if the noise is too small, then the atmospheric delay variations will map into your height variations. So, and track also in atmospheric delay models, because in aircraft, you tend to change altitude very rapidly. Track's atmospheric noise model tracking has a capability to actually allow process noise and variation in the atmosphere that depends rapidly on the rate of change of height of the aircraft as you go across. And again, the process noise units in track are basically in meters squared per unit time, and you can specify a time unit, so you can make that to be meters squared per second, for example. The benefit of doing that is if you're going from 1 hertz to 30-second sample data, for example, if you set your time unit to be 1 second, then you can use the same process noise values no matter what sampling interval that you have. So track command files use basically the same style of rules that are used in the globk command files. All the commands must start with a blank, at least one blank at the beginning. No tabs between the arguments is very important. The order of commands is generally not important, except that the later versions of command replace the previous assigned values. And then track has site-dependent commands where you issue the command name first, and then a set of lines that have the station name and the arguments associated with that station. And then generally you leave a blank line until the start of the next command after that. There's also various ways to plot track results. There's an shplotTrack script that uses GMT that can plot it, and this was one of those scripts that keeps evolving with time. For quick plots, I personally use a program which is part of Gamut-K called cplotx. It's an X Windows plotting routine with an extensive built help. It's both interactive and command file driven, and it allows you to basically specify fields in ASCII files and plot what's in those fields. It's a generic time series plotting package, does parametric fitting, etc. So it has a lot of commands, and you can, if you're running it interactively, you can get help on the commands inside of the file itself. We also use a lot of MATLAB and GMT to do these things. Just specialized scripts is very common to do that. And the important thing is the time tag that's output there comes in various forms. There's year, month, day, hour, minutes, and seconds, but we also give it fractional day of the year that you are in, and then also an epoch number, just because sometimes plotting by integer is something like 1 Hertz data, for example, is a convenient way to do the plotting. And a lot of programs can't really handle year, month, day type formats. So some just final comments as we finish this up. As I said, the most common things you change in track is the data gap that you will allow. Generally, as I've said, there's often recording problems with data gaps, and so making it larger than 1 is certainly worth it. The LC estimates and Melbourne wide lane sigmas that are allowed for the biases to be fixed, that's the S column in the F code that often gets set. You can set the correlation time that's used by track in one of the commands. Sometimes we find it just as easy to not change that and simply change the tolerances that we're using for these sigmas, with the realization that the real sigma is probably less than the one that's actually being recorded. Make sure your antenna and receiver information is correct if it is mixed. If it's not mixed and you're working on short baselines, then you can pretty much ignore all of that stuff, because it's going to cancel out in the signal differences. And then the way you treat the atmospheric delays, there can be a high correlation between the height and the atmospheric delays. And in the output, there's a column which is rho UA, which is the correlation between your up estimate and your atmospheric estimate. And if you have large process noise on the atmosphere and large process noise on the heights, you'll see that that correlation will be running somewhere around about 90% or 95%, etc. And then the weights that you give to the EX wide lane, that is the quantity that you most often change to reflect how well and how much the ionospheric variations are as you go. So again, the basic recommendation is run track in its default setting first, and then look at what comes out of the output. Based on what you see on the output, decide how you're going to tune the program, or simply say that that's an acceptable result and quit while you're ahead, as they say. Okay, thank you.